Good morning. Today, I'd like to talk about the third category of trigonometric integrals, and since this is going to be relatively short, I'll take this opportunity to talk a little bit about the inverse trig functions as well. There are three other trig identities, half of the quantity cosine A minus B minus cosine A plus B. This basically takes a multiplication of trig functions and turns it into, in this case, a difference of trig functions. There's a similar formula for multiplication of two cosine values. As before, this changes the product into a sum in this case. And lastly, if I have sine of A times cosine of B, we can do something similar with that. It's not necessary to write down a formula for cosine A sine B, because you just write this same formula down, interchanging the roles of A and B. These three facts will let us do certain types of integrals. For example, we can do the integral sine 7x times sine 4x by using the formulas that we've just described. Doing the integral is then direct. If you had cosine times cosine, or sine times cosine, you could use one of those formulas to do basically the same thing. Lastly, in this short video, I want to talk a little bit about inverse trig functions, and in particular, certain formulations that we will see again very shortly. I want to think about the graph of the sine function, the graph of y equals sine x. We all know that it is periodic with period 2 pi, has a maximum value of 1 and a minimum value of -1. When we want to construct the inverse to a function, if you remember, we interchange the x's and the y's. So the graph of the inverse function to this would be not the graph of y equals sine x, but the graph of x equals sine y instead, whose graph looks like this. Unfortunately, that's not the graph of a function. This picture fails the vertical line test, so it doesn't represent the graph of a function. What people will do is they'll say, I need a piece of this graph upon which I get all possible values of sine x, but moreover, I only want to get each value once. In that way, this graph would then pass the horizontal line test, which would make this one pass the vertical line test. The way that we do this is completely arbitrary, but since the sine function is odd, I ought to be able to get away with just taking the middle piece. I'm going to only look at x's that go from negative pi over 2 to pi over 2. On that range of x values, I do get all possible values of sine x, all values from -1 to +1, but there are no repeated function values. If I take this restricted piece and interchange the x's and the y's, I get a picture that looks like this. The name of this function is the inverse sine function, or also known as the arcsine function. The numbers that you can put into the arcsine go from -1 to 1, and the answers that you get back can go from -pi over 2 to pi over 2. The graph of the tangent function has vertical asymptotes whenever the x is an odd multiple of pi over 2. There are an infinite number of copies of this shape off to the right and off to the left. Obviously, if I interchange the x's and the y's, the resulting thing is going to fail the vertical line test, and just as with the sine, wouldn't give me a function back. If we do what we did with the sine, which is keep the piece in the middle, then I'll have a picture that looks like this. The only difference is I have to keep the x from equaling negative pi over 2 or pi over 2 because of the vertical asymptote business. If I interchange the x's and the y's, I will reflect this graph about the line y equal x. Things that were x's now become y's and vice versa. Things that were vertical become horizontal instead. Instead of having vertical asymptotes, I'll have horizontal ones instead. It's worth mentioning that there is no point on this graph where x is pi over 2. There is no point on this graph where y is pi over 2, although you can make the y-coordinate as close to pi over 2 as you like by making the x big enough. As you expect, we call this new function the inverse tangent, also known as the arctangent. Both the sine and the tangent are odd functions. Tangent of the negative of x is the negative of tangent x. Likewise for the sine. If I want to think about the cosine, things are not so nice. If I take a chunk of the cosine centered at x equals 0, extending to the left and extending to the right, my plan doesn't work this time. When I flip the graph over, it's still going to fail the vertical line test. So I can't use that same range of x values, the ones that I used for the arctan and arcsine. I need a range of x values that produce all values of cosine x, but I don't want any repeated function values. The way people usually do this is to start at x equals 0, proceed to the right until you hit the bottom of the curve for the first time. The range of x values from 0 to pi gives you all of the values of the cosine, all the way from 1 all the way to -1, and no function value is repeated. This is the chunk of the graph of the cosine that we'll use to describe the arccosine or inverse cosine. If you take the chunk of the cosine that we're using, interchange the x and y numbers, the resulting graph looks like this. On the new graph, the x can be anything from -1 to 1, and the y, the arccosine or inverse cosine values, can be as small as 0 or as big as pi. I'll leave you with a mental exercise for those who are interested. What about secant of x, y equals secant of x, which is defined to be 1 divided by cosine x, not inverse cosine x. This one really is 1 divided by something. What does the graph of the secant look like? How about the inverse secant? Since the secant's closely related to the cosine, probably you should use the same range of values as those that you used in getting the inverse cosine from the cosine function. We'll talk about this eventually, but it won't hurt any if you think about it a little bit. this is everything I wanted to say in this short little video. I hope everybody's having a good day. I'll talk to you again soon.